There we go. Can everybody hear me? All right. Well, thank you all for coming. Welcome to the USGS Evening Public Lecture Series. Not working? Hello? A little better? Is that better? There we go. Okay. So my name is William Seelig. I'm with Science Information Services. Again, this is our August public lecture. Before we introduce tonight's speaker, just a reminder about September's lecture. The title is What's in a Species Name? How Wildlife Management Relies on Modern Systematics Research and Museum Collections. It's about the Wildlife Research Center at the Smithsonian Museum in Washington, D.C. So please grab a flyer and join us all at next month's lecture. Tonight's title of our lecture is Roving on Mars, Curiosity's Exploration of Gale Crater. We have Lauren Edgar from our astrogeology program in Flagstaff, Arizona. And just a little bit about Lauren. So Lauren is a research geologist at the Astrogeology Center. She earned her bachelor's degree from Dartmouth College in 2007 and her PhD in geology from Caltech in 2013. Prior to coming to the USGS, she was a postdoctoral fellow in the School of Earth and Space Exploration at ASU. She is an active member of the Mars Science Laboratory and the Mars Exploration Rover Science Team. Her research aims to understand Martian surface processes through the use of rover and orbital observations as well as terrestrial field analogs. She uses sedimentology, stratigraphy, and geomorphology to infer past processes involving water, wind, ice, and volcanic activity, and to identify potentially habitable environments on Mars. So again, after the lecture, please hold any questions until afterward. There'll be 2 mics at the back where you can ask your questions, and please welcome Lauren.
All right, well, thank you all for coming out. Hopefully you can hear me. It's a pleasure to be here tonight, and I'm really excited to share with you some of the results from NASA's Mars Science Laboratory Curiosity rover mission and our 5 years of exploring diverse sedimentary environments in Gale Crater. So I'm a research geologist at the Astrogeology Science Center in Flagstaff, and I also wanted to point out that a lot of the work that I will show here tonight would not be possible without all of the science and engineering teams that are part of the MSL mission. So this will be a summary of some of the exciting results. And in this talk, I want to give a brief overview of the mission so far, kind of how we do operations, where we went on Mars. And then I'll give a summary of some of the distinct and unique environments that we have observed so far. And then I'll give a preview at the end of kind of where we're heading next. So I always like to start with a reminder of the primary scientific goal for the MSL mission, which is to explore and quantitatively assess a local region on Mars' surface as a potential habitat for life, past or present. So to do that, we want to characterize the biological potential, the geology and geochemistry, the role of water, and the surface radiation environment. So in my own work, I'm mostly focused on looking at the geology and geochemistry and what that can tell us about the past role of water on Mars. So to meet that goal, this is Curiosity's scientific payload. So first of all, you can see it's a 6-wheeled rover. It stands about 2 meters tall, and it's powered on the back, hanging off the back of the rover here. You can see this radioisotope thermoelectric generator. So it's basically the heat given off by plutonium decay is what powers the spacecraft. So this is the part of the talk where I get to say that I drive a nuclear-powered laser-wielding robot on Mars. But it actually has a pretty powerful scientific payload, and I'll just give a brief overview of what some of these instruments are capable of and how we use them in operations. So you can see on the rover's mast that we have a couple instruments for remote sensing. So we have our Mastcam imaging system, which consists of 2 camera eyes that are capable of full-color panoramic and stereoscopic imaging. And I mentioned the stereo imaging because we can actually use the parallax between the 2 camera eyes. And if we know the angle to an outcrop or a feature of interest, we can generate a range map. So you can use those stereo images, and then in every pixel in that image will have X, Y, and Z values. So if you wanted to look at a geologic contact and look at some structural relationships, you'd be able to kind of, plot pixels, pull those out along a surface, fit a plane to it, and that's how we actually take a strike and dip on Mars. So you're not a geologist there on the surface with your Brunton compass. We have to rely on this stereo imaging. We also have the ChemCam instrument, which uses laser-induced breakdown spectroscopy to get the elemental composition of rock and soil targets up to about 5 meters away from the rover. This instrument also contains a camera called the Remote Micro-Imager, which was initially intended just to provide context for all of those little laser shot points. But it's actually one of our more powerful cameras that we have on board. So more recently, we've been using it to get detailed grain size and textural information and to look at targets that are much further away. Then we have the RAD instrument, which looks at the surface radiation environment. And this was actually the first instrument that was turned on the mission. So right after launch, kind of in that cruise phase from Earth to Mars, RAD was collecting data to characterize how much radiation you might receive. So this is very relevant for future astronauts going to Mars, characterizing how much radiation they would receive in transit, and also it's been operating continuously on the surface. And then on the rover's arm, we have several instruments for in situ analyses. So in order to get at the bulk chemistry of a sample, we have our alpha particle X-ray spectrometer, or APXS. We also have the Mars Hand Lens Imager, or MOLLE, and this acts as a geologist's hand lens. So it's a camera at the end of the arm that you can get really close to the surface, just a couple centimeters standoff, and this provides all that nice detailed grain size information. Then we have several instruments that help us acquire samples. So we have a drill. You can see these prongs that are sticking off of the end of the arm there. We also have a scoop, brush, and sieves. And these all help us acquire sample and then pass kind of the finer grained portion of that into some of the instruments in the interior of the rover. On the belly of the rover, we have the MARDI camera. So this is the Mars Descent Imager that was initially planned to be used just during landing. But because we have a camera underneath the rover, we've actually been using that to help characterize the terrain beneath us as we've been driving. And then in the interior of the rover, we have the ChemIn instrument, that uses X-ray diffraction to get at the mineralogy of a sample. And then the SAM instrument, which is a suite of mass spectrometers that tells us about chemistry and isotopes. And then on the back of the rover, we have the dynamic albedo of neutrons, or DAN instrument, which is used to characterize subsurface hydrogen. And then also located on the rover's mast, there are a couple little booms that stick off. And this is our weather station, basically. So it's the rover environmental monitoring system. And this tells us about temperature, pressure, relative humidity, winds, in a number of different environments. In my own research, I'm mostly working with data from the MOLLE, APXS, ChemCam, and MassCam instruments to characterize past sedimentary environments. All right, and I also wanted to touch on the USGS involvement in rover operations. So in Flagstaff, we have about half a dozen folks that are involved in the daily operations of both the Curiosity rover and the Opportunity rover. So we're involved in both the uplink of commands to some of the instruments and the downlink of data, making sure that we got all of the products that we needed. But I always get questions, what is it like to work rover operations? Because I think this is perhaps what a lot of people might think rover operations looks like. Perhaps you're imagining that you're there with a joystick saying drive right, drive left, or maybe you think you're Matt Damon roving around on the surface. But in reality, this is what rover operations actually looks like. So we work a lot with Gantt charts. So here you're just looking at the timeline from left to right and then how we can actually fit all these different observations that we want into a plan. Don't worry about reading the details here, but the different colored blocks just show how we have time that's devoted for science and time that's devoted to other activities like mobility. Kind of that blue, royal blue box that you see is a science block, and within that we have several ChemCam observations that are nested. And we really need to try and fit all those science observations in against our time, power, data volume constraints, as well as telecommunications passes. So the green boxes that you see represent when we have orbiters. So we have satellites in orbit around Mars that are helping to relay data back and forth. So early on in the mission, this is what rover operations looked like. This is when the whole team was together at JPL, living on Mars time for the first 3 months of the mission. So to really maximize the science return from that initial phase, we had everyone living on Mars time, which is about half an hour longer than an Earth day. So through the 3 months, we managed to cycle through every possible time zone about 3 times over. But it was really exciting to have everyone there. And this is a meeting of the Science Operations Working Group that you see. And in my own role in operations, when I'm on duty, I chair this meeting, and it's a lot of balancing the requests that are coming in from the geology theme group and the environmental theme group, and trying to fit those in with the tactical planning day. So where do things fit with our overall objectives? What targets are going to help you meet those objectives? What instruments do you need to collect the necessary observations? And what is the relative priority of all of those activities? So we spend about a full day on Earth planning what the rover is going to do that day on Mars, and then we uplink all of the commands in a bundle at the end of the day, and then come back in the next morning and you have all this new data to work with. But these days everyone has gone back to their respective institutions, so instead of looking like this big meeting here, it's a lot of telecons actually. All right, so let's actually go to Mars. So this is Curiosity's landing site in Gale Crater. And you're looking at topography. So this is from the Mars Orbiter Laser Altimeter. And the colors, the reds and yellows represent really high areas. The blues and purples represent low areas. And you can see Gale Crater is this large crater right there in the middle that lies on this dichotomy boundary between the relatively high cratered southern highlands and these relatively smooth northern lowlands. And you can see that Gale actually represents the lowest point in this scene. That white color there is the lowest. And so the argument was made, if there ever was widespread atmospherically derived water and it flowed downhill, that Gale would represent the likely reservoir. You can also see it lies within this swath of kind of northeast trending channels going from lower left to upper right. And it's also a very old crater. So this is dated to about 3.5 to 3.8 billion years old at a time that we think Mars might have been wetter. In terms of the size, you can see it's about 155 kilometers in diameter, which is about 100 miles, maybe the distance between here to Santa Rosa. And you can see it also has this large central mound in the middle of it. So this was an opportunity to study a class of craters on Mars that all have these central mounds. We also wanted to go to Gale because looking at it from orbit, we saw some intriguing geomorphic features. So here the colors represent lines of similar elevation contours. And so if you had water in there, this might represent potential closed basins or potential areas where lakes might have persisted. And these closed contours actually correspond to interesting channel suites that come in at different elevations around the crater. And then, of course, the central mound is called Mount Sharp. And it contains more than 5 kilometers of strata. And so we wanted to go there and kind of read all the stratigraphic levels, like pages in a book, and figure out the environmental history. And if we zoom into the flank of Mount Sharp there, also prior to landing, we noticed that there were some intriguing mineral signatures based on orbital spectroscopy. So the colors here, the greens and oranges represent different clay minerals, and then the magenta and blue represent different sulfate minerals. And the clays are often indicative of aqueous environments, and the sulfates are often indicative of very acidic environments. So we're seeing potentially some large environmental change going on here that we want to go investigate in more detail. Okay, so actually getting to Mars. So Curiosity launched on November 25th, 2011. 26th, I can't read, on board an Atlas V rocket from Cape Canaveral. And we landed on Mars on August 5th, 2012. So you'll notice that's just about 5 years ago, so we just celebrated our 5th birthday on Mars. Happy birthday, Curiosity. And as you might remember from the news around that time, we had a very interesting way of approaching the entry, descent, and landing on Mars. So because Mars has some atmosphere, but it only has a thin atmosphere, we can't rely on just a parachute in order to safely slow down the spacecraft to get it to the surface. So we had to do a combination of this parachute descent and powered descent, where you're firing retro rockets, and then that's slowing you down. And then this really intriguing part of the process called the sky crane, which you see here. So essentially those rockets are slowing you down, and then when you get very close to the surface, the rover comes down, wheels fully deployed, hanging by these tethers to this landing platform. And as soon as those wheels make contact with the surface and the line goes slack, that landing platform, the cables get cut, and that platform goes and crashes elsewhere, and hopefully not right on top of your $3 billion rover. Fortunately, this all worked very well, and it made a bunch of people in blue shirts, these are the EDL engineers, very happy. And meanwhile at JPL that day, all the scientists were gathered in another room, and the engineers basically said, "Here are the keys, she's yours." So this is one of the first images that we received from Mars. This is taken from the hazard camera on the rover's chest, and so you can see the right and left front wheels there. The sun is behind us, so you're seeing the long shadow of the rover there. And then there in the distance, looming in the distance, is that mound, Mount Sharp. And some of the first words that were uttered were, "Touchdown confirmed, let's see where Curiosity will take us." So where did it take us? This is another perspective view looking at Gale Crater. The black circle there represents our landing ellipse. And prior to landing, the team embarked on this large-scale geologic mapping effort. And so what you're seeing here are some of the results showing the 6 different geomorphic units that we identified in those different colors. And where we landed is that white dot that you see, which is at the distal extent of this large alluvial fan that extends from the northern crater rim, shown in that tan and brown colors here. So this is the Rover's Traverse from where we landed back in August of 2012 to our present location in August of 2017. So you can see that we've covered more than 16 kilometers in total odometry. And the yellow line is showing the traverse, and those teal triangles are showing areas that we investigated in much more detail. I should also point out that some of the names here might be familiar from Earth names. So prior to landing, we actually divided up that landing ellipse into 1 kilometer square quads. And then each quad was assigned the name of a town on Earth of less than 100,000 people. And then as we drove through that area, any rock target that we investigated in more detail was given a name from a geologic unit or formation or feature from that town on Earth. So you'll probably see a few familiar names, but I promise you these are on Mars. So what I'd like to do in this talk, I'm just going to give a brief overview of some of the geology that we saw along this traverse, starting with when we first landed back at Yellowknife Bay. And this is one of my favorite images from Mars. So this is actually a view from orbit from the high-rise camera on board the Mars Reconnaissance Orbiter. But it's looking down on our landing site at Bradbury Landing. And you can kind of see this blue and kind of darker toned area where those retro rockets that we were firing during landing actually blew away all of the dust, exposing some of the bedrock there. And then you might faintly be able to see some rover tracks that are leading down into Yellowknife Bay. And there where that arrow is pointing is actually Curiosity glinting in the sun, smiling back up at us. So I love this image, and it also points out why we wanted to drive down into Yellowknife Bay, because it lies at the intersection of these 3 distinct geologic units. So we had the Hummocky Plains unit that you see here on the left, this bright bedded fractured unit on the upper right, and then down here on the lower right is this cratered surface. So we wanted to go down and have the opportunity to sample each of those different units. So one of the first things that we saw on Mars were evidence for conglomerates. So here you're looking at nice rounded pebbles, some hints of stratification in there. Some of these showed hints of imbrication where the clasts are lined up like dominoes. These are nice class-supported rounded pebble conglomerates. And this was really the first opportunity to investigate these and realize that we had evidence of shallow streams flowing across the surface of Mars. So this is a great welcome to Gale Crater. But of course, these were just isolated outcrops, only about 5 or 10 centimeters thick. So we had a lot of exploring left to do. So as we continued driving down into Yellowknife Bay, we approached an outcrop known as Shaler, which you see here. And we were immediately struck by these beautiful cross-stratified sandstones. So your eye can probably pick up on some of these beds that are dipping down to the left with some other cross-bedding that's superimposed on them. Then at the grain scale, we were noticing nice rounded pebbles, some of which showed these little indentations or collision marks that tell us about the bedload transport. And then at the outcrop scale, down here at the lower left, we were able to identify some outcrop length surfaces that are represented by those different colored lines that you see. And each of these beds was defined by a gravel-rich bed that fined upwards into some sandy bed forms. We were able to use that mass-cam stereo imaging technique to take some strikes and dips on these features. And we realized that these beds are actually dipping about 10 or 15 degrees to the southeast, and superimposed on that you have some nice smaller scale bed forms. So essentially we could reconstruct in a lot of detail that this was a bar in an ancient stream with dunes that were migrating along the slope of it. And all of that transport was coming from the northern crater rim. We're also able to say that the flow of that stream was intermittent, so we had kind of pulses of deposition, but at times the flow was sustained in order to acquire multiple sets of these dune-scale bed forms. So this is the first opportunity to really do a detailed analysis of a fluvial deposit on Mars. And then we finally found our way down into Yellowknife Bay. Here you have a nice image of the arm extended, and Mount Sharp is there in the background. And just as a reminder, this is that nice bedded fractured unit that we'd seen. And this was our first opportunity to really apply the full scientific payload to understanding an outcrop on Mars. So the first thing that we did is we brushed the surface to clear off the dust and see the actual bedrock underneath. And you can see here's the kind of the wire brush down here in the corner. And when we brushed that surface, we revealed a nice gray, fine-grained mudstone underneath. And this was a very soft rock. You can actually see places where we scratched the surface of the rock because it was so soft. And then we used the alpha particle X-ray spectrometer to tell us about the bulk chemical composition of both this rock and then an adjacent rock that showed some white little veins running through it. To be able to say that those other white veins that we'd seen were calcium sulfate, which are shown in the big blue peaks there. The next thing we did was we actually drilled for the first time on Mars. So this was a great day on Mars. You can see our test drill hole and then the first drill hole on another planet that was achieved robotically. And here's an example of the drill bit and then the scoop full of some of the acquired sample here. Then we used the ChemCam instrument to assess the elemental composition here of both the brushed rock, the drill hole, and the tailings. And so in that upper image, you're looking at the drill hole, and you can see some remarkable pointing in order to get those little laser shot points down into a drill hole that's about the size of a dime. Pretty impressive. You can also see one of those white calcium sulfate veins cutting through here. And then we also used the ChemCam instrument to assess kind of the drill tailings compared to some of the surrounding bedrock. Next, we ingested some of that sample into the rover to be able to do X-ray diffraction and figure out the mineralogy. So here's an example of typical sand on the left compared to this mudstone that we're investigating here on the right. And the main difference is that the drill powder contained abundant phyllosilicates. These are clay minerals that indicate sustained interaction with water. I'm hearing some wows. That's a good sign. So then we finally passed the sample into the SAM instrument, and this is just one of the experiments that we run where you basically heat up the sample and measure the volatiles that come off of it. One of the cool things here, if you look at that red curve, you're seeing water that's released early, but then also water that's released at high temperature. And that high temperature release of water indicates water that was bound up in clay minerals. So collectively, this all provides a lot of evidence for the first habitable environment that we were able to investigate on Mars. So the regional geology and fine-grained rock suggests that this site was at the end of an ancient river system or within an intermittently wet lake bed. The mineralogy told us that we had sustained interaction with liquid water, that was not too acidic or too alkaline, and it was low salinity. So basically, if you were there on the surface when this water was present, you would be able to drink this water. We also found evidence for the key chemical ingredients for life, such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and the presence of minerals in various oxidation states that would provide a source of energy for primitive organisms. So within the first couple months of the mission, we'd already achieved our goal of characterizing habitable environments, so this was a huge success. And I wanted to show kind of how we can apply that full science payload to investigate different sites, because we've now done this about 15 times, and I won't go into the detail on all of those. But this was an exciting place to start, but we still had a lot left to explore. All right, so looking back at our traverse path, pretty much everything between Yellowknife Bay and this area that I've circled, along the plains here, we noticed a lot of cross-stratified sandstones and conglomerates, basically evidence for a lot of shallow stream flows as we'd seen early on. But in the vicinity of this area called the Kimberley, things started to look a little bit different. So from orbit, this was an area that we'd identified a new geologic unit that's shown here in the blue that we called the orbital striated unit. And that's because from high-rise images, you can see the arrows point to a couple of these different outcrops. You might be able to faintly see some lineations that trend from kind of lower left to upper right, which is southwest to northeast in this image. And these are remarkably consistent over many kilometers where this is exposed. And at any given place, it's exposed for about 50 or 100 meters that you see these lineations. Here's just a rose plot showing that consistent trend. And so this was going to be our first opportunity to go and characterize this on the surface. However, around this time in the mission, we started to notice a lot more wheel wear than we had expected to find on Mars. So these are some holes that are not supposed to be there. which is basically telling us that a lot of the rocks that we were driving over were much harder than we anticipated. They were much better cemented. They were eroded by the wind into some really sharp, pointy rocks. So we needed to change our drive strategy. We had been driving on the topographic high areas because it gives you a good vantage point, but suddenly we needed to start driving in these topographic low areas, these valleys, because the sandy cover provides more protection for the wheels. So one of the places where we first made that turn to go down into a valley was at this place called Dingo Gap. And we basically had to drive up and over this little transverse wind-blown bed form here to get down into what we call Moonlight Valley. But the advantage to the geologists from having changed our drive strategy is that suddenly you're driving through valleys with beautiful exposures of several meters of stratigraphy on either side of you. So this actually worked out quite well for us. And as we drove into Moonlight Valley, one of the first things we noticed lower in the section, again, were our familiar cross-stratified sandstones, some evidence of small-scale ripples and dunes, some nice pebbly sandstones there, all indicative of transport by shallow streams. But then higher in the section, we noticed these conglomerates. And these are poorly sorted, weakly stratified, and we're starting to compare these to what we'd seen with the previous conglomerates. And these looked a little bit different. For one, they contain clasts of other sedimentary rocks. So here are a couple examples of other sandstone clasts that got ripped up and incorporated into this conglomerate. So this is telling us we had a high energy event. We also noticed some subangular clasts up to about 6 centimeters or so in diameter. So this is really, like I said, high energy fluvial event and different conglomerates than what we'd seen early in the mission. So when we look at the distribution of these conglomerates, here I've outlined in white where they occur in these different lenses that we see here. And we actually recognize that these are discrete channel bodies. So previously we'd mostly seen evidence for unconfined flow, probably sheet floods, but suddenly we're starting to notice discrete channels. And taking a closer look at those, we realize that the conglomerates are incised into some underlying sandstone beds, a couple of examples there. And so this is telling us about some event that is really drawing that gravel front basinwards. So it suggests some sort of high energy event, a drop in base level or perhaps lake level that we would expect to find downstream. So as we continued driving, we wanted to keep an eye out for potential evidence of that lake level drop downstream. So there are 3 main outcrops that we looked at. So I just showed you Dingo Gap and Moonlight Valley. And then as we drive towards the Kylie and Kimberley areas, this would be our first opportunity to characterize that striated unit on the ground. So we got to Kylie. This was the view. So you're looking towards the east and keep an eye out for things that might look like those striations from orbit that we suddenly started realizing corresponded to these south-dipping beds that are dipping to the right in this image. So this is your ooh and ah moment, so I will run through that one more time as we pan across Mars, and you can imagine that you're standing there on the surface. There we go. All right. So this was a beautiful scene, and we realized these correspond to south-dipping beds. And there are even a few places where we noticed small deltas that were migrating southward. So this is a cute little delta where you can see some of these top sets that are rolling right over into 4 sets. And then as we continue driving into the Kimberley area, we recognize the same thing. So here you're looking towards the west-southwest, so all of those striations from orbit actually correspond to beds that are dipping to the left here. And again, seeing evidence for those small-scale deltas, where top sets, again, rolling right into 4 sets. So this is the first place that we really recognize this delta cliniform geometry. So previously in the mission, most of the stuff that we saw corresponded to kind of river processes. And now suddenly we're in this more transitional area recognizing slope processes and small-scale deltas. And all of this is predicting that as we keep driving deeper into this basin, further into the basin, that we would expect to find some lake deposits. All right, so to summarize on our traverse path, everything we saw early on I've labeled as fluvial, meaning shallow streams and rivers. Then we're in this kind of transitional period around the Kimberley, where we saw evidence for deltas. And now we're going to take a look at an area called the Pahrump Hills and then an area called Hidden Valley. Here's just another orbital image looking down on those. This is some nice color data from the HiRISE camera. And you can start to see a different geologic unit that's cropping out here, kind of that lighter tone tan unit that you see in a few places. So we drove down into Hidden Valley, and sure enough, we finally found our beautiful, fine-grained, evenly laminated almost rhythmically laminated deposits that are reminiscent of lake varves. So we finally found our lake deposits, and this was very exciting. And there were even places where you can see these lake deposits that are overlain by fluvial and deltaic deposits. So looking at this section as a whole, you see some nice thin laminated mudstones overlain by more thickly laminated or thinly bedded sandstones and up into cross-bedded sandstones. And as we continue driving, this is an area called Pahrump Hills. Again, we saw those beautiful, fine-grained, evenly laminated lake deposits. So we finally have evidence for a long-standing body of water on Mars. And so putting that all together, this is kind of the environments that we found, from fluvial to transitional into this lacustrine, meaning lake deposits. And pretty much everything that we've seen for the last 3 years of the mission has been more evidence of those lake deposits. But it would be a pretty boring talk if I just showed you evidence of fine-grained, evenly laminated rocks. So instead, I'm going to focus on some of the more unique things that we have seen through this section. All right, so I should have pointed out, too, that there's all of these dark features that you see here correspond to dark basaltic sand dunes, and these are active wind-blown sand dunes. So we had the opportunity to go and look at these and study active wind-blown sand dunes and current processes on Mars. So again, this is a high-rise orbital image. All of those lake deposits that I showed you are part of the Murray Formation. We'll talk about the Stimson sandstone in a bit. But before we got there, we kind of found this gap in the dunes where we could safely bring the rover in, not get trapped in the sand, and investigate some of these dunes. So one of the first images that we acquired was this gorgeous shot of the Bagnall Dunes. So here your eye is probably just picking up on some of those multiple scales of bed forms that we see here. And we were able to back the rover right up to the lee slope of one of these to be able to assess some of the morphology of this dune in more detail. So here we're just comparing the morphology of the dune to things that we see on Earth. Some of the similar processes, we're seeing evidence for grain flow, areas of grain fall. I've just labeled the brink, horn, and toe of this dune, all very similar to wind-blown dunes that you see on Earth. And there were other areas where we were actually able to use the wheel and kind of scuff into the dune. This is our way of trenching into it to compare what we see on the surface to some of the stuff that's underneath, look at details of the grain size and composition. But the other thing that I wanted to point out here is the multiple scales of bed forms. So on Earth, we're probably used to seeing these nice little wind ripples that are superimposed on a larger scale dune. But what's different here on Mars is this intermediate scale of bed form. Here's a couple of these that are labeled that have kind of meter scale wavelengths. These are still small ripples, only a couple centimeters tall. But they have sinuous crest lines, very asymmetric profiles. And this is actually the result of a different process on Mars. So we call these fluid drag ripples, and they're the result of Mars having a much thinner atmosphere. So it's pretty cool to go to Mars and see something that's completely different from what we see on Earth. We're also able to do change detection experiments. So this is using the hand lens imager at the end of the rover's arm, looking down on one of these ripple crests. And here, a couple of the areas that are circled are areas that you might see some change as I flip back and forth between these two images. So these were taken about 3 minutes apart, and you can actually see some little sand grains that are saltating by. So pretty cool to see these active processes on Mars. But we're not just looking down at the rock and soil. We're also remembering to look up sometimes. So in light of last week's great American eclipse, I wanted to show you a solar eclipse on Mars. So Mars has two moons, Phobos and Deimos, which are both thought to be captured asteroids. And we sometimes look up and see the transit. Here's a transit of Phobos crossing the sun. And by observing these events, we're actually better able to characterize some of the orbital parameters of these moons. Pretty cool, but we're not going to capture totality here. These are tiny moons. I think Phobos is about 14 miles across or so. Okay, and with the remainder of the talk, I'll just go into some of the other additional weird geology features that we've seen in this part. So starting around this area called Marias Pass. So I showed you before, all of those lacustrine mudstones were part of the Murray Formation. But here at Marias Pass, we recognize for the first time this very sharp unconformity with the sandstone that overlies it. When we take a closer look at what we've called the Stimson Formation sandstone, we see beautiful sets of climbing dunes here. And taking a look in even more detail here, this is just annotated, showing some of those nice sharp truncations, those set boundaries between different sets of dunes here. The white is highlighting the foresets, so this is able to tell us which way the dunes were migrating. We can look at the geometry of the crossbedding to reconstruct the shape that these dunes might have had. And interestingly enough, some of the details even reveal these small-scale ripples that correspond to that new unique bed form that we saw on Mars. So this is telling us that at the time that this sandstone was deposited, the atmosphere on Mars was already much thinner. So again, here's just a schematic diagram reconstructing what we call the Stimson Formation, which is a dry Aeolian dune field, meaning wind-blown dune field. And so based on the geometry of the crossbedding, we can say that these dunes had sinuous crest lines. We don't actually see any evidence for inner dune deposits, so we know this was a pretty dry environment when this was laid down. This is also just depicting that unconformity with the underlying Murray Formation, shown in purple there. And using kind of the dip direction of all these foresets, we can reconstruct that the paleotransport direction was towards the northeast, which is actually the opposite direction from the modern wind-blown Bagnalled sand dunes. So pretty cool to be able to compare both modern and ancient environments at the same time. And then as we kept driving, this is through an area called the Murray Buttes. Most of the buttes, all of the kind of steep cliff faces, were made up of that Stimson Formation sandstone, and everything that we were driving on, this nice tan color here, represents the Murray Formation mudstone. But we started to notice some differences in the Murray Formation. So rather than that nice, evenly laminated mudstone that I showed you before, we've recently started noticing evidence for what we call ripple cross-lamination. So this is telling us that we're getting into shallower water, or shallower lake deposits, or perhaps some evidence of streams and rivers entering this lake. And this is just compared to an example from Earth of the Triassic Moenkopi Formation on the bottom there. We also started noticing some large-scale crossbedding, and this is in the Murray Formation. This was the mudstones before. We're now suddenly noticing what might be evidence for wind reworking of some of those sands. And then we have beautiful examples of desiccation cracks. So here you're looking down on a bedding plane and noticing all of these little polygonal fractures at kind of the centimeter scale that tell us that we had repeated wetting and drying. So suddenly we're either getting to more marginal parts of this lake or into shallower water. All right, so to summarize all these environments that I've shown you, we have this block diagram that's just a schematic of the different sedimentary environments, and then in the foreground, kind of this cross-sectional view, the different groups that we were driving through with the rover. So the red line represents Curiosity's traverse path. Essentially on the top surface, what you're seeing is that we had erosion of the northern crater rim that carried water and sediment in these shallow streams kind of into the basin here. At times we had lakes that were present. These were, noticing variations in lake level through time, but we had deltas that kind of marked the extent of that lake. Sometimes we had some nice dune fields around the margins there. But essentially what Curiosity has seen was all of the evidence for shallow stream deposits. Then we approached those delta deposits, and then we spent much of the last 3 years exploring these lake deposits. And the squiggly lines, zigzags that you see there show that at any one time those environments were kind of interfingering as we're filling in the basin. So the regional summary here in text is that we had erosion of the northern crater rim that generated gravel and sand that were transported southward in shallow streams. Over time, the stream deposits advanced towards the crater interior, which transitioned downstream into finer-grained, southward advancing delta deposits. These deltas mark the boundary of an ancient lake, or lakes, where mud-sized sediment accumulated and infilled both the crater and the internal lake basin. However, we know that occasionally there were drops in base level or lake level that are inferred from those incised channels, and also that we had intermittent dry periods that were recorded by these Aeolian, meaning wind-blown sand of the fluvial and lacustrine lake deposits. So this artist's representation here on the bottom just kind of shows going from dry to wet to dry conditions, noticing that we had those fluctuations. But the really cool take-home story is that based on the thickness of sediment that we've seen in these lakes, we know that we had long-standing periods of water on Mars for probably anywhere from hundreds to tens of thousands of years. So it's been a pretty exciting journey so far. And then with the remaining time, I just want to point out where we're heading next. So this is a mass cam image looking up that mound, Mount Sharp. So in the foreground, the dark band that you see, those are those wind-blown sand dunes. The Murray Formation were all those mudstones. And today on Mars, we were actually investigating the hematite ridge. So you can see kind of this pinkish, reddish color associated with that. And we have our eyes on the clay unit and then the layered sulfates beyond. And looking at how that plays out with the overall mission so far, so we spent the prime mission, those first 2 years, we were mostly investigating those shallow stream deposits and getting into our first real lake deposits at the Pahrump Hills, with the exception of Yellowknife Bay early on. Then in the first extended mission, we spent most of that investigating that Murray Formation, all those mudstones with a little bit of that Stimson Formation separated by the unconformity. And now we're really starting the climb here. So I should point out this is 14 times vertically exaggerated. So we're not actually climbing slopes that are that steep. But it really does highlight how much of this mound we're really climbing. And so today on Mars, we're at that red arrow investigating that hematite unit. And we've been doing some reconnaissance. So this is, again, a mass cam image in the upper left compared to a high-rise orbital image of the area that was targeted. And you can see that using that ChemCam remote micro imager, and this is a mosaic of about 10 of those frames stitched together, we can really bring out a lot more detail in the mound and look at some of the bedding geometries that we might see there. And we're also using Masscam to do that. So here's a beautiful Masscam view looking at some of the bed thicknesses and bedding geometries that we might see. Another ooh and ah moment. And then I will just leave you with this week on Mars. So this is our traverse path right up to this hematite ridge. This is the ridge that you can see cutting through here. And basically we're right at that blue star, and we are planning our drives kind of up this shallower part of the slope to be able to investigate this hematite unit. And as we're driving up, this is our view, and we are doing some systematic sampling along the way, looking at variations in chemistry and sedimentary structures that we see in these locations. So we'll end on that and just say that it's been a lot of fun to be along for the ride, and I'm looking forward to the next 5 years, hopefully, of exploring Gale Crater. So thank you very much.
Thank you, Lauren. And now we'll open it to any questions from the audience. Again, for the benefit of our streaming audience, if you have a question, please use one of the mics up here, or I can bring you this handheld mic as well.
So thank you very much. There was a beautiful shot of the rover with one of its wheels. You said it was abrading, digging. I assume you were not there holding the camera at that time. And so did you cheat on the image, or how did you do that?
Great question. I keep forgetting to point this out. So that is taken with the camera at the end of the rover's arm. And it's actually not just one image that allows us to take that selfie. It's dozens of images that are stitched together. And they're stitched together in such a way that you can stitch out the arm because you have other coverage of that area. So no, we're unfortunately not standing there on the surface taking that image. But it's a great way, by taking these selfies, of kind of documenting, how the rover is doing, and also these investigations that we do in more detail.
Okay. Thank you. That was amazing. So 2 questions. One is I could easily see, could you do the rest of your entire career with this? I mean, it is so cool. But you hear of these things going on and on. But the real question is, have you seen anything like folding or any of the other things that we see in sedimentary formations and other larger signs of motion like that, large scale?
Yeah, so we haven't seen any large-scale structural deformation, but at the small scale we have seen some soft sediment deformation. So really water lane, sediment, kind of fluid is escaping. So more on the tens of centimeters scale deformation. Good question.
With the atmospheric pressure as it is today, how much of a gap is there between the freezing point and the boiling point of water? Or is there any gap?
So that's a great question. So actually a lot of surface conditions on Mars exist at that triple point of water right now. So it's at exactly that point.
So there's not much prospect for keeping liquids around.
Exactly. Pretty challenging.
So great talk. Thank you very much. What's the sort of time scales upon which you plan? It sounded like the very next day's drives are sort of discussed and programmed in just the previous day. Is that typical? I mean,
Great question. So we plan at a couple different scales. So something like this large-scale campaign where we want to investigate this ridge that has the hematite signature, we've been planning that for months, actually, of, what will we do when we get there? What's the best traverse to get up there? Then we also plan at kind of the week-long scale. The long-term planning role on the team is looking at what we call the SOL path. Monday, Tuesday, Wednesday, Thursday, Friday, what are we doing each of those days? But we really come in tactically and can make complete changes to that plan based on the data that you receive the day before. The drives are usually, we try and have a good head start on where you'd want to plan things. So we do our full planning day, and then at the end of the day, we call it N+1. So what's tomorrow going to look like? And we can put some placeholders for activities in there. You can start to think of where exactly you want to be driving. But it really does require all of those different scales of planning.
I just had a general question, a couple of them. So what is the rover made of? And also, if there's mechanical parts, how does the maintenance take place with all the weathering the elements?
Great questions. I don't know all of the materials that are present. We obviously use aluminum, things that are lightweight but also have, some structural integrity, but, all sorts of different insulating materials as well. In terms of mechanical maintenance, unfortunately, we can't do any. So when an issue comes up, it's going to probably stay that way for the rest of the mission. So instead, we start coming up with creative solutions to work with something in that new configuration. Unfortunately, if software issues come up, we can upload new software and make those changes, but mechanical issues are hard to come by. I should also point out we have the wheel wear under control, so don't worry, those wheels are expected to last for many more years and help us up this climb, but it was just an interesting find early on.
So this is kind of two questions. One's the housekeeping, along the lines of you're saying if things break, you don't get to fix them. How do you keep the lenses clean on all these equipment and the cameras, right?
Yes, great question. So I showed you that image where we had the looking down at the ripple crest, seeing little saltating sand grains, and that made the instrument PI for that camera very, very nervous that day. So we have a dust cover that covers over the MOLLE instrument, and so sometimes you can image through that, but for some of these, we will allow the dust cover to be off, take the image, and immediately close it.
Got it. And the other question is, when you're looking at these amazing photographs of the sediments and things like that, and you've got an angle to a lot of these sediments, how would you tell if there's some seismic influence there, or there's no way it's seismic, it's all based on the mechanics of falling downhill? How would you know what you're looking at?
Yeah, fortunately Mars has helped us out, and there are certainly enough very planar flat surfaces that are in between some of these inclined beds that we see the cross bedding in, and so you wouldn't be able to just deform one part of that section without deforming all of it if it was due to earthquakes or other structural deformation. And also the angles that we're seeing for some of these inclined beds are all things that are consistent with primary depositional slopes. So nothing really out of the ordinary with that.
Thank you.
Thanks.
You've done a lot of study of the chemistry of the soil of Mars. If and when Homo sapiens ever arrive at Mars, is there a chance that they could do any chemistry that would extract air or water from the surface?
Ooh, good questions. And I don't know the answer in detail. I don't know if someone else wanted to comment on that, but in terms of extracting water on Mars, so water on Mars is hard to come by. There's subsurface ice that we've noticed in more of the northern regions, but the water that we're finding here is just tiny amounts of water that are bound up in minerals. We've been looking for CO2 frost in Gale, but there's not a whole lot of moisture if you went to a place like this in the equatorial regions. So you'd probably have to extend your reach to more of the higher latitudes in order to find that.
Yeah, okay. So if nothing forces a stop on this, what's the potential life expectancy of the whole system? How long could it keep going unless something collapses and blocks it?
Great question. We obviously hope forever, but I mentioned that the power for this rover is a plutonium source, and that source is decaying over time, meaning that we are getting less and less power from it than we did early on in the mission. So some studies suggest that around year 7 or 8 that we might start to notice a significant drop-off in the power that we have available to do operations. So it's not saying it's going to end then, it's just that we will notice the impact on operations. So, hopefully 10 years, hopefully more, but keeping in mind that our power will be the limiting factor, I think.
Two age-related questions. How do you tell how old a crater is? You mentioned the age of the Gale Crater. And then how long ago do you think there was bulk water on Mars?
Good question. So the age of Gale Crater was based on crater counting. So based on the number of craters that a given surface acquires over time, and scaling that actually with dates that we have from the moon, from the Apollo samples that were brought back. That's the best that we can do right now on Mars is crater counting. So Gale is thought to be about 3.5 to 3.8 billion years old, and a lot of these environments that we're investigating within Gale we think probably occurred shortly after its formation. So also thinking that that water was kind of upper 3.5 and above in terms of the age. Good question.
Since we know there was water on Mars, are we able to say that the water left or went underground or evaporated faster in this location versus that location, like the equator versus the poles versus hills versus valleys? Is there anything that tells us the water stayed around longer in this area and went away really quick in that area?
That is a good question. So the question was, is it possible to say that water went away in different parts of Mars at different times? We know that it was once wetter. Did it all disappear at the same time, or were there regional variations? I'd have to defer back to the geology that we're seeing here that tells us for sure that we had water flowing across the surface. You'd really want to compare that to a bunch of other places on Mars and know those relative ages. I'm not really sure, other than that, if there would be a way to tell. Probably require a lot of modeling as well. So we know that Mars used to have a thicker atmosphere, and that a lot of that atmosphere has escaped. That's actually something we've been able to measure using the SAM instrument on MSL, looking at deuterium to hydrogen ratios, and essentially proving that we had a thicker atmosphere early on. So in terms of figuring out regional differences, though, I think the geology would just be the way to go.
Back to another operations question. I imagine something like Hubble is very oversubscribed in terms of people wanting to do experiments on it. And is something similar happening to the rover in terms of just way more people have, I want to do this, I want to do that, I want to do that, and just not time, or we got to get moving or whatever? How's that sort of boil out?
Yeah, so I would say we have a ton of data that's been brought back from Mars that anyone that wants to can go and look this up. If you actually go to this JPL site, you can look at all of the new raw images that come down. They're posted within a day or so. And also the Planetary Data System, the PDS. We systematically, every 6 months or so, will put all of the chemistry data and from all the other instruments. That is all made publicly available. So there's a ton of data to work through that a lot of people could be working on. But in terms of the actual time that the rover has each day to do operations, you are fighting for that time. Like each day, even the geology theme group compared to the environmental monitoring theme group is fighting over the same limited resources that we have that day on Mars. So
you're running that meeting?
Yep. Believe me, it's fine. Not just trying to balance scientist requests, then you have to balance the science requests against what the engineers are telling you can or cannot do. So it's always fun.
Question, you have a really nice schematic. It's a sort of a 3D wedge. Yeah, right there. Could you tell me, two questions. How far deep have you gone, or do you plan to go down into the bottom of that lake bed? And how far up on those craters can you go? Can the vehicle go?
Good question, and something that I didn't have the chance to point out here, I'm just going to change slides really quick, is that we've actually been systematically driving uphill. So I was talking about getting deeper and deeper into this basin, but that's really deeper into the different environments that we're seeing. even though we've been climbing uphill. So at any one time, you probably had rivers moving into deltas, moving into a lake. But then you kind of filled in the crater a bit, and then the next successive, group of rivers moving into lakes, moving into deltas. And so it's showing the progressive infilling of Gale Crater. But we've mostly been driving uphill that whole time. And so we can't really, unfortunately, answer the question of how deep into the basin could you get. But in order to address kind of how high we're planning to climb, let me see if I have a good, maybe I don't have a good image here at the end. We certainly hope to get through these different clay and sulfate units, and I guess that would kind of be up through some of these layered deposits that you see through here. So we've currently climbed maybe about 250 meters of total elevation gain, and I think we want to get to 400, 500 or so.
My question's a little bit along the lines of what the gentleman over there asked. I was just wondering, so you found evidence that there was some kind of water on the surface of Mars, but have you found geological evidence that shows like how it might have left, and will you be able to find something like that?
Evidence of water leaving. So I guess in the case of the lake deposits, obviously evidence for evaporation leaves, behind these desiccation cracks or evaporite minerals, or salt crystals that you might see on the surface. But that just, could vary locally. So I think the question was really large-scale Mars losing its atmosphere, losing its water. The water is currently tied up in the polar caps. But I don't know what evidence you would be able to look for exactly to say this is when this happened. So it's a good question I'll have to think about more. Thank you.
I have a question. First of all, thanks for a wonderful talk about the longer-term strategy. As I recall, when Gale Crater was selected, a great deal was made of Mount Sharp and the ability to climb up Mount Sharp. And the first 4 or 5 years, you spent chasing sedimentary activity, wonderfully productive. Was this adapting to what you were finding, or how did that change in strategy, or was it a change in strategy?
Absolutely. So on our traverse path, you might have noticed that we took a little jog into Yellowknife Bay early on. And so this little change was not planned. So essentially, we landed here. We knew we wanted to get to all of these units where we saw those intriguing mineral signatures. But no matter what, we're going to have to drive around the Bagnall sand dunes. So we don't want to get the rover stuck in the sand. So we were always kind of shooting for this same gap through here. But in terms of the timeline and how long it might have taken to get there, that was because we were getting distracted with some awesome geology along the way. So, you're not going to pass up the opportunity to characterize the first habitable environment on Mars, just to say, get on the road, get to the mountain. So it was kind of a mix of both.
My question has to do with spacecraft design. Your rover was designed years before you actually got to Mars, and it has all kinds of great instruments on it. What have you learned that would help future missions? Have you had somebody say, gee, I just wish we had thought to put that instrument on that we didn't have? Or is there any instrument that you have that you say, gee, that isn't turning out to be as useful as I thought it would be?
Good question. I think for this mission that the instruments that we have are very well suited to the science objectives. But if, for example, you're really after looking at organic minerals, for example, you might change. For the Mars 2020 rover, we have instruments that are capable of doing Raman spectroscopy. So I think it really goes back to what is the objective of the mission. These are well suited. I'm excited to see new results from different instruments on 2020. Other than saying put some heftier wheels on that, I don't know. There's too many lessons learned of how we would change that. Thank you.
Thank you for a great talk. It seems like Gale Crater was chosen because there was all these unique features in there. Would you be able to extrapolate this to the rest of Mars, or is this specific to a particular area that you've found?
Good question. So I think through some geologic mapping, you might be able to identify nearby some other similar features. But this is a lot of the detailed geology that we've been doing just tells us about this local area. It's certainly encouraging to find such diverse sedimentary environments here and long-standing evidence for aqueous alteration. And so that would, you would presume that you would find that other places on Mars as well. But it's hard to say that exactly these same environments might be present in the next crater rover.
Thank you. One more question. So on the operational side, you said something about batching instructions and sending it over so that it can execute the commands the next day. What about like day-to-day operation, minute-by-minute operations, if it were? Like, as you're driving through, are you getting feedback at different points to decide that this is not a path I want to go forward on and I want to change things around? Or is it always something of a planned route that it follows?
Yeah, so unfortunately, based on the signal delay between Earth and Mars, which varies based on where Mars is in its orbit from a couple minutes up to about half an hour, we can't do real-time observations. So it's not, you're not just sitting there waiting for the image to come down. We really do plan a full day on Earth and then see what, upload those commands at the end of the day, kind of carries it out over our nighttime, and you come in the next morning to new data. And so I mentioned that the Martian day is about half an hour longer than the Earth day. And so we're no longer living on Mars time, but we do need to kind of adjust our schedule to when we can get those orbiter passes to give us new data. And so sometimes we have to start really early in the morning or start kind of later. And when our schedule gets completely out of whack with Mars, we have a skip day and trying to catch back up to it. So that's how we deal with Mars time these days, which is much nicer than round the clock. But unfortunately, it's not real time.
Thanks.
Thank you.
A couple more questions, if you'll indulge me. Sure. You mentioned that the retro rocket actually excavated pits of some kind and exposed some bedrock. Did you want to actually take that opportunity to look at the bedrock, or was it contaminated by the exhaust, or was it just too difficult to climb down or up?
So it didn't really excavate pits as much as it blew away all of the dust, revealing some of that nice bedrock underneath. And the first things that we saw certainly looked like those conglomerates that I showed as we drove away a little bit, but I think we were initially a little hesitant, what kind of alteration might that have, might that caused, to some of these rocks. So we looked at them, thought, hey, that looks a lot like a conglomerate that was deposited by a shallow stream, but we really wanted to confirm that with some unaltered rocks nearby.
And those are beautiful pictures you have. I assume that they're true color, so how did you do the color balance?
Good question. You'll probably notice in a few of these the sky on Mars looks a little blue, which is not true. So the sky on Mars is actually reddish, kind of dusty. And so this is just the particular white balance that's been applied to some of these, which is a helpful color stretch for looking at the geology, but just keep an eye on the sky is not necessarily true to form.
Pretty informative. I really liked it. I have a couple of questions. One is how do you determine that there is no water underground? What will be the probe that you need to use to see that not just the surface water, but also underground there is no water?
Yeah, so we're actually using the DAN instrument, the dynamic albedo of neutrons. It's a neutron spectrometer that can tell us about subsurface hydrogen. But again, that's modeling a lot. So you kind of have to say, okay, if we model this depth and this amount, can we match some of those results that we're seeing? And for the most part, the results that we've seen in Gale Crater are mostly dry. And so that's how we can answer that here. But yeah, that's a good question for elsewhere on Mars.
Another question is that, is it possible that our devices also carry some microbes there so it can part of the environment, Mars environment? How do you make sure that it's completely sterilized? It didn't carry any microbes there.
Great question. So this falls under planetary protection, and we know that we have a somewhat dirty spacecraft. So there's different levels of how clean your spacecraft has to be based on whether it's going into Earth orbit or Mars orbit or the Mars surface where water might be present. And one of the things that I actually have to do in my role as this, Science Operations Working Group Chair is each day I'm asked, is the plan clear for planetary protection? Meaning if we take our somewhat dirty, it's a pretty clean spacecraft, but it still probably has some Earth microbes on it. If we take that anywhere near what looks like, current ice or water or something, that would be a violation of planetary protection. So unfortunately or unfortunately, we have not seen any evidence of current water, ice on the surface here. So that's something to keep in mind, though.
So there's no contamination.
Right. We don't want to bring our dirty Earth microbes to Mars.
So has there been any effort made, like you mentioned that, to also look into the microbes that they might be there? Because we are finding out on Earth, there are species which can exist in a very, very harsh environment, especially in the ocean, in a very harsh temperatures and pressures. So is there a possibility that Mars can have that as well?
I mean, I guess it's always a possibility, right? And you would hope that maybe some extremophiles might be able to take hold here. But unfortunately, a lot of the surface environment that we've seen on Mars is, dry. It's super arid, oxidizing, acidic, unfriendly conditions for life at the surface as we know it. So, maybe if there were modern microbes on Mars, they might be deeper underground. But certainly something to keep an eye out for.
I'm back to your planning meetings. Are they webcast for public viewing?
So the question is if the planning meetings were webcast for public viewing, and unfortunately they are not. You can't listen to us all sit around and argue. But the documentarian reports that kind of record how some of those planning decisions were made, that's all made public on this Planetary Data System, PDS website. So you can't listen to the meeting, but you can kind of look through and see what are we doing today on Mars, what are the observations that made it in, and any major changes to the plan.
Thank you.
Back to this gentleman's question about, we were going to climb up Sharp, but we spent all this time wandering around in the flatlands, and it was great. But did you actually land where you wanted to? In other words, had you wanted to land closer to that bridge across the dunes?
So all we knew is that we were going to land somewhere within that landing ellipse. So we, everyone on the team had kind of X'd out a spot where they're like, I predict that we will land here. I got pretty close, actually. But, you would hope that anywhere in there, it's safe. We didn't know the exact traverse that we would need to take. We knew that crossing the dunes would be a challenge, but if we had landed further downwind in our landing ellipse, we would have been around the side of it anyway. So that wasn't really something that we could control. But, I think we got pretty lucky because we were right next to Yellowknife Bay and were able to characterize a habitable environment. If we hadn't really seen that, we might have been driving across the plains for a lot longer.
I think we're getting pretty close to closing here, so rather than make a question, I'd like to make a couple of statements. We here in Silicon Valley tend to be science-oriented. But I think that I do speak for the group here in saying that we feel that NASA is really spending our tax dollars well. And so thank you for faithfully following that initiative.
Well, thank you for the support and for all of you for following along on this exciting mission. Really appreciate it.
And secondly, you're probably the closest thing to a true space explorer that we'll ever meet, making decisions about exploration in the Lewis and Clark tradition.
Well, thank you.
So
it's
thank
been
you.
a lot of fun. Thank you.
Again, thank you all for coming. Thank you, Lauren. See you all next month.